So today we're interviewing Luca Benini. And Luca, I wonder if you could just tell us a little bit about your work and maybe the relationship to Boole's work.
Yeah, that's a pleasure. So I work as a professor in a University of Bologna in the Swiss Federal Institute of Technology in Zurich. Mostly I'm working in the area of digital integrated circuits and the systems. And in my line of job, we have everyday dealings with Boole's legacy. Basically, we are working with digital circuits that are working with zeros and ones, and Boolean algebra is the root of what we do from the theoretical viewpoint, and also with it's not only a remote theoretical link, but it's quite a live legacy, quite a live link, and it shows itself in a lot of things that we are doing, in the sense of optimizing digital logic for real physical implementation, for chip manufacturing and chip design. And we always have to go and reconsider what are the fundamental underpinnings of the Boolean theory and apply them onto the reality of the physical transistors that we are using for implementing Boolean circuits.
So Boole did this very early on. So I wonder what your view was on that time, what kind of a leap his inventions were.
Okay. For me, what is really astonishing is the capability of building a very powerful and rich theory from a couple of very basic theorems and theoretical intuitions. So what we do in engineering is really try to replicate that. So creating a small set of simple and well understood building blocks and rules for assembling them. And using these simple, well-defined building blocks and rules, we can create larger and larger systems. Now, the key point is simple and well-defined. And I think this is where the quantum leap by George Boole is. He found a way to formulate logic and mathematics using the simplest number system, the simplest representations. Zeros and ones are even much simpler than the numerical bases we use in everyday's work and in our brains. And I think we are taught in our brains to use. And I think this is really wonderful, because this is what made this basic theoretical work so important in practice. It's a building with very, very simple elements and being able to construct on them. So it's a constructive theory based on very simple elements. And I think this is really wonderful and really nice and elegant as well.
So how long do you think it might be taught towards the future in universities or elsewhere?
Okay, so I think that it's how can I say? It's not only important in universities. I think it should be taught, and it's really important that people get familiarized with this as soon as possible. I believe that the fundamentals of Boolean algebra can be taught to elementary school children. There is no problem with that because it's so simple. Okay. And this is really something useful because it's an easier way to reason about things and to have logical thinking really inscribed into the mind of young people even before they get to university. So in my personal case, in my personal experience, I got taught Boolean algebra in high school, and was kind of unusual path in high school, because usually in a scientific high school you get taught real analysis, real valued analysis, calculus, and I was lucky that my teacher at that time decided to make this parenthesis on Boolean algebra, and even though I didn't have any in-depth mathematical culture, I grasped the concept immediately. I still remember how appealing was to being able to construct a complicated reasoning without knowing complex theorems, without having to do a lot of self-training exercises like you have to do in calculus. So I believe that through elementary school and high school, Boolean algebra, the basics of Boolean algebra can be taught. I also think that it's also important that this is very well understood in the university, but in my view, it should be really fundamental knowledge, not only taught in engineering schools or mathematical schools, because it's simple, clean, and really useful in everyday life. It teaches you a very simple and consistent way of thinking.
Do you think there is still more room for applications of logic towards the future in engineering?
Absolutely. And so I'm always kind of amazed how rich is the spectrum of things that you can do with starting from basic Boolean algebra. So maybe I can go through a couple of examples which I believe are things that are on the boundary of being explosive game changers in the future of science and also society. So I guess one which is really fascinating to me is probably most of the people know that right now there is a big emphasis on using techniques in brain-inspired technologies, so techniques coming from taking inspiration for the workings of the brain to actually deliver the next generation of artificial intelligence, the one that is used by the Googles and by the Facebooks of this world to deal with the huge amount of data that we are producing in the web every year. And these techniques are really now getting to the point in which you have enough data that you can, for example, train enormous neural networks and achieve capabilities of recognition, for example, of images, sounds, voices that are unparalleled with respect to the previous state of the art, as well as competitive with humans. So, casting aside for the time being how scary it is to have a machine that can compete with humans on human-specific tasks like seeing and listening, but let's assume that this is good, but it's going to happen. And what is really interesting today is that most of the theoretical work that is done on this field is based on real calculus, real valued calculus. For example, all the learning algorithms are expressed as gradient search algorithms using real valued functions. Now, the interesting thing, if you think about it, is that first you use this very rich algebra in real valued functions to train these classifiers and recognizers, and then you have to embed the result of the training into digital logic. And digital logic is actually binary and has a very strong, there is a very strong correlation between the amount of precision you need to represent a number and the amount of power and energy that you need to process this number. So today we are just overshooting it. We are saying, okay, let's do all the training of a neural network using double precision numbers, which basically is a 64-bit numbers, and then we are going to have a very accurate results. There is a mounting evidence in the science community that this is an extreme overkill. So, for example, you can have extremely well-performing networks that use only 16-bit of precision, which is 1/4 of double precision. And you can imagine what is the impact in energy efficiency, in power, and so on. But there is a clear evidence that you can go down much more in precision. Now, what is interesting there is that if we can go down toward a more discrete representation of this information, then we can have a huge amount of savings and in terms of power consumption, energy, and be extremely much more energy efficient. But on the other hand, our problem is less and less approximated, is less and less cast as a real valued function optimization and more as a Boolean function optimization. So I think there is a phase transition there where if we can achieve, for example, a way to learn and to train neural networks using Boolean formulations instead of using continuous valued functions, we could achieve enormous quantum leap in terms of energy efficiency in classifiers, recognizers that are coming up in our lives. Today they are in data centers. And if we can achieve what I was mentioning before, they will be very soon in smartphones, in watches. So this is an example of how, really a deep understanding of the relationship between Boolean algebra and continuous functions, continuous algebra, could bring another quantum leap for humanity.
Okay. So do you think the same logic will always be used, or do you think for the mind you will have to adapt the logic? Or
okay, so I think there is one area where there is a really significant potential for somehow extending the expressiveness of Boolean logic, and it's basically at the boundary between the work of Boole and the work of Shannon. Okay, and essentially the key idea there is if we acknowledge that the physical reality of the circuits and systems that we are using for manipulating Boolean information is subject to noise, fluctuations, errors, and then we are not dealing with our design problems by considering perfect Boolean logic, Boolean functions, by considering the gates and the circuits that we implement as perfect, idealized representations, physical embodiments of the Boolean abstraction, then if we relax this, if we acknowledge that gates make mistakes, logic gates in reality may make mistakes, or even more than the gates, memories, Boolean memories, storage is subject to errors, then this is where really we can get a more complete and realistic understanding of the, let's say, implementation gap between a theoretical formulation in Boolean algebra and a circuit that implements the Boolean algebra formulation. So in a nutshell, I think that the most important extension to Boolean algebra is modeling errors, acknowledging the probability of errors within a Boolean computation, and also extending the theory of Boolean logic to deal with uncertainty. And this is actually most of what the key intuition of Claude Shannon in his work. So relating the representation of information with the probability of errors, and how to deal with, how to provide useful results in terms of computation, in terms of communication, when you are dealing with Boolean logic in the presence of errors. So I think that this is one of the key theoretical enhancements that are really important to be understood. I'm not saying that this is something new. It's something that is around, has been around for 70 years, but it's really sometimes a bridge that is done too late in teaching and in learning. So people learn the idealized version of Boolean algebra, and then they learn the compromised version, or they learn the idea of errors, treatment of probabilities of errors, and so on much later. I think that will be extremely nice to merge these two theories earlier on, and I think it's understandable, and I believe that this is one important area.
It's interesting that Boole's second part of his book is about probabilities, but obviously I don't think he ever considered errors in that context. But yeah,
and if you look forward in the future, the way technology is evolving, let's say implementation technology, silicon technology or post-silicon technology, whatever will come in 10 years from now. If you look at that, the fabrics that we are going to use to implement the computation in integrated circuits are more and more susceptible to errors, simply because they are scaling down in dimensions to the atomic scale. And at the atomic scale, there is no certainty. I mean, there is the, Heisenberg principle and all these type of things. And when you're handling a few electrons, errors are a fact of your life. And this is what is happening with silicon, has been happening for, or already 10 years now, and it's every generation we move, there is a more struggle in maintaining this illusion of perfect silicon fabric. Now, the more we move to soft materials, like computing using biomolecules or computing using non-silicon fabrics, that are potentially more scalable or even more energy efficient than silicon, even assuming that this technology will happen, will overcome the economic hurdles that any new technology has to overcome before becoming mainstream. This technology doesn't promise to have perfect accuracy, to bring back the illusion of perfect accuracy. Actually, it's even more susceptible to errors and noise than silicon technology today. So I think that we really need to deal with that. And the more we train engineers and the more we train researchers to think in this way, the better we'll be for the future.
Does that mean there will be a bigger role for verification, or is the problem somewhere else?
Yeah, I think it's verification is, it's going to be extremely important also because we need to redefine what verification means. Today, if you think about traditional design practices in digital logic, verification is proving the equivalence in the Boolean sense between an implementation and the specification. And this equivalence can be, the proof can be automated or semi-automated, but at the end it becomes a Boolean equivalence checking. And now this is exactly where I think we have a problem, because in a probabilistic circuit, a circuit that makes mistakes, you cannot prove equivalence. The answer will be no, there is no equivalence. So these traditional Boolean-based proof techniques are breaking down. Now, today, what we try to do is let's try to put more and more design margins in our circuits so that the likelihood of the error becomes so small that we can neglect it. And this is not subject to verification anymore. But I believe that the next generation of verification engines should provide results not in terms of proof of equivalence, but of probabilistic proof of probabilistic equivalence to some degree of probability. Okay, and the degree of probability should not be only related to the fact that it's impossible to test all the possible conditions. So probability of having equivalence in 99.9% doesn't simply mean that you haven't tested 0.1% of the configurations, but it could mean that there are possibilities that the circuit, even if it's correctly specified, will compute wrong because of noise, because of uncertainty in the fabrication process. And then dealing with the circuits that cannot have deterministic behavior, but must have a probabilistic behavior, and bounding these probabilistic errors to a level that still allows the circuit to achieve a useful function and to meet the final specifications in terms of usefulness and functionality, it's really, in my view, an area that needs a lot of work. Sometimes research and development goes in waves, and waves of things that are fashionable and things that are unfashionable. And so I really hope that I have kind of the feeling after let's say the 90s and the early 80s and 90s, where most of the people working in hardware design, verification, and so on had a very strong training in Boolean algebra and how to describe logic circuits using Boolean algebra and so on. Right now, due to the complexity of the systems that you have to design as a digital designer, as a system-on-chip designer, this part of the fundamental training is being given less and less emphasis, and you tend to deal with larger and larger problems and systems and raising the abstraction level and so on. And at the end, you end up, and I see it in my PhD students coming up, you end up with students that maybe can understand how a multiprocessor works, but they have a lack of fundamental understanding of what are the foundations, the underpinning of why a microprocessor works, and so on. So I think that there is a risk that because of complexity, we move too fast to higher abstraction levels that are not so strongly based on theory, and they are somehow ad hoc formulations that people patch together to deal with the complexity. And then at the end you are skating on very thin ice, because if you don't have a strong theoretical background, things break down, and then you spend your time patching things instead of building up from solid ground. And so I think I would like to emphasize that there is a risk to consider Boole's work and his legacy something obsolete or something interesting for the sake of historical representation, while I think it's really still very important, very relevant.
Thank you very much.